let's talk about modeling. So the general idea of a model is you're trying to come up with a simplified description of something so that you understand how changes in one thing are going to influence changes in something else. And you're hoping that your model is simple enough that you can actually make one, but also precise enough that the predictions that it makes are useful. You might have done models in the past in prior math courses, and they often are things like, let's try and model the temperature of a lake as the function of time, or let's model the temperature of your coffee cup as a function of time as it cools off, or let's model the population of fish in a pond. And there are versions of this that are, of course, useful. I want to try and take a broader view. So there are lots of occasions for which modeling might be helpful. So, you've been in restaurants and periodically you'll see posted on the wall a maximum occupancy. So what is a maximum occupancy for a restaurant? Why even have such a thing? Do you know? I think it's about how rapidly people can evacuate. I think it's about if your room is over full and there's an emergency, it will be unsafe for people to evacuate. So if the thing that I'm interested in is how fast could I evacuate everybody in the case of a fire or another emergency, the first step of modeling is to try and think of what numerical quantities might affect the thing I'm interested in. What might be relevant to evacuation rates. So take a minute, pause the video, brainstorm. So usually an initial brainstorm will come up with a lot of things, some of which are precise, easy to measure, some of which maybe are less precise, maybe you can't measure them, maybe it's not clear how to make equations out of them. Here was the list that we made the first year I did this project. So people said, all right, things that are relevant. How fast do people move on average in an emergency? And then we thought, well, wait a minute, how fast people move maybe isn't just a constant number. Maybe it depends on how many people are in the room. It depends on the density of the people, because if there's a lot of people packed in, maybe they can move less quickly. And how many exits there are, how big the exits are, how crowded the room is with other furniture. Maybe a useful thing to measure if we were going to run an experiment is to see how many people can exit every 10 seconds through a door, so some type of measurement of exit rate. So if we wanted to try and come up with a single number for what's a safe maximum occupancy, there are a lot of potential factors that are related. And in order to make a model, we would want to try and describe the relationships between these factors using equations. So we're not going to do this model right now. I just wanted to illustrate a little bit of the perspective that we're coming from. Let's think of another one. Should California eliminate speed limits on the highway? You can imagine a debate about this. On one side, let's try and come up with a reason why yes. Well, maybe we feel like cars have improved safety measures, and maybe we think that there is value in individual freedom beyond safety. Like, we don't want a paternalistic state that's protecting us from ourselves. People should be allowed to make the choice to go as fast as they judge is safe. Maybe you think that's a strong argument. Maybe you don't. On the flip side, there's a fairly clear reason, I think, why you might not want to do that. It's the danger that there will be more accidents and therefore more injuries and potentially more deaths. Okay, well, how do you bring this debate to the next level, to a level beyond just, well, I think that there's going to be more accidents? Because what will someone on the other side say? Well, yeah, maybe a little bit, but not that much. How do you start to quantify your feelings? How do you start to try and make more objective predictions about something that you think will probably happen? Mathematical modeling. So you start with a human question. Should California eliminate highway speed limits? And you ask what numerical quantities are related to what we're trying to predict. So what we're trying to predict in this case might be something like, how many more deaths do we expect, or how many more crashes do we expect, or how many more injuries do we expect? So what other variables might affect this number we're trying to predict? Maybe things like this. And this number, it sometimes takes a while to try and come up with what are the right what are the right quantities that would let us easily predict the thing we're interested in? I thought, well, all right, what causes accidents? It's when people can't stop fast enough. So we could try and make a model for the stopping distance as a function of speed, because if you're going faster, you require a greater stopping distance. And so if we have a model that tells us the stopping distance people require, and we also know what people's average follow distance is, that would let us maybe try and start quantifying how frequently do we think people are likely to crash into each other if the speeds are increased. And so again, once you've started to identify some variables that you care about, you try and write equations that express relationships between your variables, and that's your model. So that process I just described is theoretical modeling. You're trying to break your scenario down into pieces and describe how the pieces are related using theoretical reasons. But just because you can make a bunch of equations doesn't mean those equations are accurate, doesn't mean they're useful, doesn't mean they're correct. You always have to make simplifying assumptions whenever you're modeling. So we can't, we'd have to assume that the room is empty, or we'd have to assume that the furniture is regularly spaced. You can't model everything down to the smallest detail. So part of what we'll talk about is how you can increase your confidence that your model is useful. But I wanted to point out there's a whole other side to modeling. You could do experimental modeling. And sometimes you do a mixture of the two. Frequently, you do a mixture of the two. But if I wanted to determine the safe maximum occupancy for a restaurant experimentally, you could imagine a bunch of different experiments you could run. One thing I might try is, let's find 25 different restaurants with different square footages. I'll get my team of people, my team of researchers, and we'll for each restaurant, we'll try and run a bunch of drills with more and more and more people to figure out what's the largest number of people who can be in that space and still exit in less than 1 minute. Or you could choose whatever time frame you wanted. And this would give us a bunch of data points. The x-axis would be the restaurant area. The y-axis would be the maximum number of people who could exit safely. And that would give us a bunch of points, and we could try and fit a function to that data. And you've done a lot of fitting curves to points. So this is another perspective on how you can do models. So our activity for today is we're going to try and do a simple model that doesn't have an obvious application or purpose, but it will serve our learning function of being able to practice modeling. My question is, if I am looking through a paper tube, what area can I actually see looking through the paper tube? And there are a lot of things that seem related to this. So the one variable that I'm going to choose as my independent variable is what distance d am I standing from the surface that I'm trying to view. So it seems like as I step backwards and I put my eye to the paper tube, I should be able to see a larger and larger circular area on the board. So what is this function that relates the area on the board to the distance I'm standing? And we're going to try it in two different ways. You'll actually collect some experimental data, and we'll try and fit a function. That'll be our model. And for homework, we'll try and derive a theoretical model just based on our knowledge of geometry. So in just a second, I'll show you how to fold the paper tube. I'd like every team to collect 6 different distance measurements. Everybody should use units of inches. I'm sorry. You should hold your paper tube parallel to the ground and perpendicular to the board so that you can actually see a circular area rather than a skewed circle like an ellipse. You're not going to be able to actually measure the area in square inches. So think about what could you measure instead that would be least prone to error. And then finally, you want to record your data in a Google Sheets so that we can share it. So I've given away what I think is the answer to this to the fourth question. I think it's probably going to be easiest to measure the diameter that is in your viewing window. So you can hold the paper tube to your eyeball. Your partner can be by the board and can slowly move objects such as their fingers into one side or the other side until the person with the paper tube says that they can see both.